In this section, we'll be looking at the integration method using partial fractions. In pre-calculus, you learned how to combine two rational functions that were being added by finding common denominators to add them. The method of partial fractions is basically reversing this process and breaking one function into two or more. So let's take a look at the general process for creating partial fractions from a more complex rational function. Our first step is going to be to divide the fraction if it's an improper fraction. Then we'll have basically a whole number part and a remainder. Once we've divided the fraction, if that's necessary, we're going to factor the denominator, and then we're going to create smaller fractions that have the factors of the denominator as their denominator. If I have a linear factor in the denominator, let's say x plus a, I must have a function that's a over x plus a. If this is raised to some power n, in addition to this one, let's call this a1 over x1 or x plus a to the first power, I must also have a factor a sub 2 over x plus a to the second power, and continue on until I have a sub n over x plus a to the nth power. So for instance, if part of my denominator was x plus a to the fourth power, I would actually create 4 of these partial fractions. Okay, the same applies for quadratic fractions, quadratic factors. If this is one of my factors, I'm going to need a fraction that is b1 and c1 over the whole thing, ax squared plus bx plus c plus some other b2x plus c2 over a x squared plus bx plus c. And I just continue until I have m factors. Whatever this power is, I've got to have one fraction for each of the powers from 1 to m. Okay, let's look at some problems that use this method of partial fractions. Okay, we'll start off simple and work a problem that has only distinct linear factors. Here's our problem. I could see right away for this function that it's not an improper function, so I can go on to the next step of factoring the denominator. So I'm going to get a over x plus 2 plus b over x plus 3. Okay, these two factors are different, so each one only appears one time, and so that's all I need to do. The next step is to multiply this equation by this least common denominator, which is x plus 2 times x plus 3, which will give me a times x plus 3 plus b times x plus 2 equals 1. Okay, I know this is going to be true for all x. So what I can do is choose values of x that will help me figure out what a and b are. So I'm going to start off with x equals -3. When x equals -3, this is going to be 0, and a is going to go away. And I'll have -3 plus 2 is going to give me -1. So negative b equals 1, which means that b must equal -1. Next, I'm going to choose x equals -2. That's going to make this factor go away. And -2 plus 3 is going to be +1, so I'll just have a equals 1. And so my decomposition is going to look like this. I'm going to have 1 over x plus 2 minus 1 over x plus 3. Okay. Now I have two simpler fractions that I can integrate a little more easily than the original. In this example, we'll look at a function where I'm going to have multiples of the same linear factor. I start off with this function, 5x squared plus 20x plus 6 divided by x cubed plus 2x squared plus x. Okay, and because this highest power here is less than this power here, this is not an improper fraction, and I can proceed to factoring the denominator. So when I factor that denominator, I can factor out an x, and I'm left with x squared plus 2x plus 1. Just rewrite our numerator up here. And now I see that this also can be factored. I'm going to write this as x times x plus 1 squared. Now I'm going to break this into partial fractions. My first fraction is a over x. Then I'm going to have b over x plus 1. And then because this is repeated, I need to have c over x plus 1 squared. Okay, again, I multiply by the common denominator. So the a gets multiplied by x plus 1 squared. So b has to be multiplied by x and another x plus 1. So I'll have bx times x plus 1. And then the c is only going to be multiplied by x, so it's just cx. And then I'll have this numerator, and the denominator will cancel out on this side. Okay, to solve for a, I'm going to let x equal 0. When x equals 0, this is going to be 0 because of that. This is going to be 0. This is going to be 0. This is going to be 0. So I have a times 1 squared. a times 1 is equal to, the only thing that's not 0 on this side is the 6, so a must equal 6. Now I'm going to solve for c by letting x equal -1. So when x equals -1, this is going to be 0. Because of this, this will be 0. And I'll have c times -1. So negative c. On the other side, -1 squared is +1, so I'll have 5. This will be -20. And then this is just 6. So here I'm going to have -9 equals -c, so c equals +9. Okay, now I've used the best numbers I've got to find a and c. There's not really a convenient number that's going to help me with b by canceling out both of those. But what I can do is I can just pick any number for x. I already know what a and c are, so I'll put those in as well. So let's use x equals 1 this time. Okay, so in this case, I'm going to have 1 plus 1 is 2, squared is 4 times the value of 6. So that's going to be 24 for this term. In this term, I'm going to have b times 1 times 2, so plus 2b. And then c times 1, well, c was 9, so that's going to be plus 9. And on this side, 5 times 1 squared is 5. 20 times 1 is going to be 20. And 6. So this side is 31. Here I've got 24 plus 9, so 33 plus 2b equals 31. And we can see that b equals -1. So to write my integration problem now, I could say that the integral of 5x squared plus 20x plus 6 over x squared plus 2x squared plus x. Now I can take my original function and rewrite it as a 3-part integral with simpler functions. And that's going to look like this. I'm going to have 6 over x, that's the a part, minus 1 over x plus 1. Okay, that was our b part, plus 9 over x plus 1 squared dx. When I integrate this, I'm going to get 6 times the natural log absolute value of x minus natural log absolute value of x plus 1 plus 9 times x plus 1 to the -1 over -1 plus a constant. And then combining, I get the natural log x to the 6th over x plus 1. minus 9 over x plus 1 plus my constant. In this example, we'll be looking at a function that has both linear and quadratic factors, but no repeated factors. Here's my original problem. Okay, I see that this factor can be broken down again, so I'm going to rewrite it. Just take that x out. Like that. Now I'm going to write my partial fractions. Notice I've got to have cx plus d because this is a quadratic factor. And that's equal to my original integral. And I'm not going to write that out again. But let's multiply by the least common denominator, which will give me a times x minus 1 times x squared plus 4 plus b x times x squared plus 4 plus cx plus d times x plus 1, and all of that equals my numerator, 2x cubed minus 4x minus 8. Okay, to find a, I can see that letting x equal 0 will zero this out, and we'll also zero out this one. So let's do that. We're going to say x equals 0, which gives me a times negative 1. A 0 here will give me 4, 0, 0, and this is going to equal 0 here. We'll eliminate that and this. And so all that's left is negative 8. When I divide by negative 4, I get that a equals 2. So I'm going to make a little note here. A equals 2. And now work on B. And this should have been minus 1. If this is minus 1, this factor is here and here. So if I let x equal 1, this is all going to zero out. This is all going to zero out. So I'm going to have b times 1 times 1 plus 4 is 5 is equal to, well, this is going to be 2 times 1, so 2 minus 4 minus 8. So I'm going to have 5b equals negative 10, And then when I divide by the 5, I get b equals -2. Now I have values for a and b, but I still need to find c and d. To do this, I'm going to have to pick another couple of values for x and solve a system of equations. So I'm going to start with x equals -1. And if I choose that, I can combine that with b equals -2 and a equals +2. And I'm going to get -6 for my original here is equal to 2 times -2 times 5 plus -2 times -1 times 5 plus -c plus d times -1 and -2. Okay, and all that boils down to 2 is equal to -c plus d. So we want to save that equation. Now I'm going to let x equal 2, b is still -2, and a is still 2. And I'm going to have 0 equals 2 times 1 times 8 plus -2 times +2 times 8 plus 2c plus d times 2 times 1. Okay, and that simplifies to 8 is equal to 2c plus d. So this is the second equation for my system. With this system of equations, I can solve and find that c is equal to 2 and d is equal to 4. Now I can write my new integral. Here's the original. Here's my new integral divided into smaller chunks. When I integrate, I get minus natural log absolute value of x minus 1 plus natural log of x squared plus 4 plus 2 arctangent x over 2 plus the constant. In this last example, we have a quadratic factor that's squared. So we're going to still have to do two partial fractions, one for x squared plus 2 by itself and one for x squared plus 2 squared. So let's look at this problem. I'm going to start out with ax plus b over x squared plus 2 plus cx plus d over x squared plus 2 quantity squared. Okay. When I multiply by least common denominator, I'm going to get ax plus b times x squared plus 2 plus cx plus d. This is the common denominator, so there won't be anything else there. And that equals my original denominator, 8x cubed plus 13x. Make that a little neater. Now I'm going to multiply this out, which gives me ax cubed plus b x squared plus 2ax for this plus 2b plus cx plus d equals 8x cubed plus 13x. Okay, now I'm going to compare like terms. I have ax cubed equals 8x cubed. So a must equal 8. I have bx squared, but on this side I don't have any x squared term. So that means that b must equal 0. For my linear terms, I have 2ax here and cx. So 2ax plus cx must equal 13x. And then I have 2b plus d for constant term, but there's no constant term here. I already know that b is 0, but this tells me that d is also 0. The only thing I really need now is the c. So let's go back to 2. I know that a is 8, so I'll put 8 in there instead. 2a, so 2 times 8 times x plus cx equals 13x. So c must be -3. So let's write all of our numbers down that we know. A is 8, B is 0, C is -3, and D is 0. So now I'm going to rewrite my original integral. It will be 8x over x plus 2, x squared plus 2, plus negative 3x over x squared plus 2 squared. And then dx, of course. When I integrate, I get 4 times the natural log of x squared plus 2 plus 3 over 2 times x squared plus 2 plus my constant. Okay, just as kind of a summary for this section, here are the steps that you should use when you're working with partial fractions. For linear factors, you're going to substitute the roots of the distinct linear factors into your basic equation. For repeated linear factors, use the coefficients determined in the first guideline to rewrite the basic equation. Then substitute other convenient values of x and solve for the remaining coefficients. For quadratic factors, we're going to have to expand the basic equation, collect the terms according to powers of x, and equate the coefficients of like powers to obtain a system of linear equations involving a, b, c, and so on, and then solve the system of linear equations. Okay, this is a many-step process, but it's not a difficult process. This is all math that you've done before.